We've learned the methods to find the two-port parameters in the previous lectures. Now we will introduce how to find the equivalent circuit of the two-port network with its parameters. These two questions are inversible. Firstly, you should know the concept of the equivalence. The meaning of the two equivalent two-port networks is that for the external circuits, they have the same voltage-current relationship at each of the two ports. It should be emphasized that equivalent refers to that for the external circuits, they are equivalent. Usually their internal circuits are different. For example, this two-port network is connected to the external circuits, but we don't know its internal structure. If we can construct a two-port network which has the same voltage-current relationships at each of the two ports as this network, then this two-port network constructed by us is equivalent to the original one. Firstly, let's focus on the equivalent circuits of the reciprocal two-port. These are G parameters for a reciprocal two-port. Since it's a reciprocal two-port, G12 equals G21, and there are only three independent elements. So we can use the T-type or pi-type network to generate the equivalent circuit. Reviewing the example when we introduce the G parameters, we know that pi-type network might be easier. Okay, suppose we use such a pi-type network to be the equivalent network of the original one. We need to determine the three resistances to ensure that this network, two-port network, has the same voltage-current relationships at each of the two ports as the original one. We can find the G parameters of this two-port. Letting port 2 be short, we get G11 prime and G21 prime. G11 prime equals GA plus GB, and G21 prime equals I2 over U1 equals minus GB. Since it's a reciprocal two-port, G12 prime equals G21 prime. Letting port 1 be short, we get G22 prime equals GB plus GC. Since this two-port network should be equivalent to the original one, they must have the same G parameters. In other words, GA plus GB equals the former G11. GB equals a former G21, and GB plus GC equals the former G22. Then we can find these three resistances or conductances. With these three conductances, we can get the equivalent circuit. We can see the solution of the equivalent circuit for the reciprocal two-port is relatively simple. Several notes. First, although we use a pi-type network for the G parameter here, in fact, the T-type is also applicable. For the external circuits, T-type or pi-type are all equivalent. Secondly, if G12 equals G21 and G11 equals G22, which means the original two-port is a symmetrical one, then the equivalent pi-type or T-type network should be symmetrical too. So GA equals GC here. Thirdly, you must remember that such a T-type or pi-type network is only applicable to solve the equivalent circuit of the reciprocal two-port. How to find the equivalent circuit for the non-reciprocal two-port networks? We need to use the dependent sources. Take the R parameters as an example. We can directly get its equivalent circuit consisting of the dependent sources according to its parameter equations. Examine the equations type. U1 equals R11 times I1 plus R12 times I2. U1 is the sum of the two items. It has a form of the KVL. U1 and I1 are the voltage and the current of the same port, so their relationship can be represented by R11. Here are I1 and U1. U1 is the sum of the two items, and R11 represents the first item. For the second item, since U1 and I2 are the voltage and the current of different ports, we need to use a current-controlled voltage source whose voltage equals R12 times I2. Then we get the first equation. Similarly, we can deal with the second equation. U2 and I2 are the voltage and the current of the same port, so this item can be represented by R22. For the other item, it's a current-controlled voltage source, whose voltage equals R21 times I1. This is the equivalent circuit for the general two-port network containing the dependent sources. If G parameters are given, we can process in a similar way. I1 is the sum of the two items. It has a form of the KCL. This is a reference direction of I1. Since U1 and I1 are the voltage and the current of the same port, their relationship can be represented by G11. For the second item, since I1 and U2 are the voltage and the current of different ports, we need to use a voltage-controlled current source, whose current equals G12 times U2. The voltage-current relationship of port 1 is satisfied then. We deal with port 2 similarly. Since I2 and U1 are the voltage and the current of different ports, we also need to use a voltage-controlled current source, whose current equals G21 times U1. Since I2 and U2 are the voltage and the current of the same port, their relationship can be represented by G22. The voltage-current relationship of port 2 is also satisfied. You can see there are two dependent sources in the equivalent circuit. In real circuits construction, a dependent source is very complicated. Usually active elements are needed, such as op-amps. They will greatly increase the cost of the circuit. So we should decrease the number of the dependent sources in the equivalent circuit as far as possible. For example, can we only use one dependent source to generate the equivalent circuit? Let's have a look. We firstly make some changes to the parameter equations of the two-port. This is the parameter equations of the general two-port. Since it's not a reciprocal two-port, its G12 isn't equal to G21. Then we transform the equations. I1 still equals G11 times U1 plus G12 times U2. Since G21 isn't equal to G12, we can set I2 equals G12 times U1 plus G22 times U2. So we need to plus G21 minus G12 times U1. Let's look at the new equations. For the first part, these two coefficients are same, so it represents a reciprocal two-port. According to the above contents, we can use such a pi-type network to generate the equivalent circuit. How to represent the second part? Since I2 and U1 are the voltage and the current of different ports, we can use a voltage-controlled current source to represent it. Its current value equals G21 minus G12 times U1. This is the equivalent circuit of a general two-port network with only one dependent source.